The dealer flips one card face up. You see a king of hearts. Now the probability of the other cards changes. The face-up card gave you information. Conditional probability updates your beliefs based on what you've observed. P of a given B equals P of A and B divided by P of B. You restrict the universe to outcomes where B occurred, then ask how often it also occurs. From a standard deck, P of heart given red card equals 13 out of 26 equals 1/2. Knowing the card is red narrows the possibilities from 52 to 26. Of those 26, 13 are hearts. The denominator, P of B, is the restriction. The numerator, P of A and B, is the overlook. Two events are independent if knowing one tells you nothing about the other. P of a given B equals P of A. Successive coin flips are independent. The coin has no memory, but gene expression levels are not independent. If gene A is a transcription factor for gene B, knowing it is high makes B likely high. Testing for independence, the chi-squared test compares observed joint frequencies to what you'd expect if the variables were independent. Deviation from independence is the foundation of correlation, mutual information, and co-expression analysis. The law of total probability decomposes P of A into exhaustive scenarios. P of A equals P of a given B1 times P of B1 plus P of a given B2 times P of B2, summed over all partitions. For a diagnostic test, P of positive test equals P of positive given disease times P of disease plus P of positive given no disease times P of no disease. That's sensitivity times prevalence plus false positive rate times 1 minus prevalence. This formula is the denominator in Bayes' theorem. Bayes' theorem falls directly from the definition of conditional probability. P of a given B equals P of A and B over P of B. P of B given A equals P of A and B over P of A, and solve for P of A and B from the second equation and substitute into the first. P of a given B equals P of B given A times P of A divided by P of B. Rename. What's here equals likelihood times per divided by evidence. This is the derivation the weather forecaster video used without proving. Prior, P of A, your belief before data. Likelihood, P of B given A, how likely the data is given each hypothesis. Evidence, P of B, the normalizing constant. Posterior, P of a given B, your updated belief. A disease has 1% prevalence. Test has 95% sensitivity and 95% specificity. You test positive. What's the probability you actually have the disease? Most people guess 95%. Bayes says, P of disease given positive equals 0.95 times 0.01 divided by 0.95 times 0.01 plus 0.05 times 0.99. That's 0.16, 16%. Most positives are false positives because the disease is rare. This is the base rate fallacy from the p-value series episode 3. And it's why screening tests need high specificity when prevalence is low. The casino runs on probability. Sample spaces define what's possible. Random variables quantify outcomes. Expectation and variance describe the distribution. Conditional probability updates beliefs. Bayes' theorem formalizes the update. The base rate determines whether a positive test means anything. Know these rules and the house edge shrinks.